Have you ever wondered if the most interesting places in space are the ones we often overlook? We tend to focus on the massive planets, yet the smaller bodies orbiting them hold their own distinct mysteries. They are not simply rocks floating in the void. They are diverse environments that operate under their own sets of rules. It is a complexity that hides behind a simple point of light. This detailed yet calm observation is the focus of sleep astronomy. If you appreciate a clearer view of the cosmos, a gentle like and subscribe helps the channel grow. For now, relax as we shift our focus to these distant, orbiting worlds. The universe is a vast and complex structure where new information is constantly revealed. As we look outward, we embark on a survey of distinct celestial environments, ranging from the volcanic terrains of Io to the quiet, familiar craters of our own moon. Our observation extends to the atmospheric compositions of distant exoplanets like K218b, the frozen nitrogen landscapes of Triton, and the magnetic complexities of Ganymede. We are moving through a catalogue of celestial wonders, venturing beyond well-charted territories to examine potential habitats and enigmatic worlds that challenge our standard definitions of life and planetary formation. We invite you to analyze the mechanics of these bodies and consider the implications of their existence. It is possible that we are close to understanding mechanisms that have operated in silence for eons. Time and further observation will provide the answers. In the broad expanse of our solar system, amidst the massive gas giants and frozen satellites, there exists a world so volatile and extreme that it forces a re-evaluation of planetary science. This is Io, the innermost of the 4 large moons orbiting Jupiter. From a distance, this moon appears shrouded in tranquility, yet it holds a level of energy that colors its surface in vivid shades of red, orange, and yellow. It is not a dormant rock, but a celestial body caught in a state of permanent geological revolution. In terms of size, Io ranks as the 3rd largest satellite of Jupiter and is slightly larger than Earth's moon. However, unlike our moon, which is geologically quiet, Io is involved in a continuous gravitational interaction with its parent planet and its neighboring moons. This interaction is effectively a cosmic tug-of-war. Io is locked in an orbital resonance with 2 other large moons, Europa and Ganymede. For every 2 orbits Europa completes, Io completes 4. And for every 1 orbit Ganymede completes, Io completes 4. This precise timing forces Io into an elliptical or oval-shaped orbit rather than a perfect circle. As Io moves closer to Jupiter, the planet's immense gravity pulls hard on the moon. When it moves farther away, the gravitational pull weakens. This constant variation creates enormous tidal forces within the solid body of the moon. To understand the scale of this force, consider the ocean tides on Earth, which are caused by the moon and Sunday. On Io, the solid ground itself creates tides. The surface of Io physically bulges up and down by as much as 330 feet during a single orbit. This is not water moving. It is solid rock shifting height by the length of a football field. This relentless flexing generates tremendous friction deep inside the moon. Just as bending a metal wire back and forth causes it to heat up, the kneading of Io's interior generates massive amounts of thermal energy. This heat melts the rock and creates a global subsurface ocean of magma. Consequently, this gravitational process ignites the most spectacular volcanic phenomena found anywhere in the solar system. Io is the most volcanically active body we have observed. There are hundreds of active volcanic centers scattered across its surface, Some of these eruptions eject plumes of lava tens of miles into the thin, waterless vacuum above. Recent observations, including stunning images captured by NASA's Juno spacecraft during its 51st flyby of Jupiter, have revealed this fiery process in high resolution. These are more than aesthetic images. They are data points that help us understand how tidal heating works. When we view these active landscapes from the perspective of Earth, we are reminded of the diversity inherent in our solar system. The environment on Io is a stark contrast to the blue, water-rich stability of our home planet. On Earth, volcanism is largely driven by internal heat left over from the planet's formation and the decay of radioactive elements. On Io, the heat is actively generated by its orbit. This results in a surface age that is remarkably young. While the Moon itself formed about 4.5 billion years ago, the surface we see today is likely no more than a couple of million years old. The constant outpouring of lava resurfaces the Moon, burying any impact craters left by meteorites. Instead of craters, we see lakes of molten lava and smooth floodplains of liquid rock. The geological features on Io often take the form of depression calderas, known as patera. These are distinct from the cone-shaped volcanoes often seen on Earth. They resemble vast cauldrons pressed into the crust. Sometimes, lava flows spill out from these depressions, and at other times, explosive interactions blast material directly upward. The chemical composition of this lava remains a subject of scientific analysis. Some models suggest the flows are composed of silicate rock, similar to basalt on Earth, but at extremely high temperatures. Other theories propose that the flows consist largely of molten sulfur and sulfur compounds. This sulfur hypothesis explains the varied coloration of the Moon, as sulfur creates different colors, from yellow to red to black, depending on its temperature. This composition stands in contrast to terrestrial volcanism. On Earth, distinct volcanoes like Mount St. Helens or Mauna Loa define the landscape. Mauna Loa, the largest active volcano on Earth, has a caldera less than 4 miles wide. On Io, the scale is vastly different. One of the most significant features on this moon is Loki Patera. This is not merely a volcano but a massive lava lake, effectively a sea of molten rock. It is the most powerful heat source on the Moon, responsible for approximately 10% of Io's total thermal output. Loki Patera is a depression more than 125 miles in diameter. To provide a sense of scale, an eruption from this single feature could produce enough lava to cover an area the size of the state of New Jersey. The behavior of Loki Patera is periodic and complex. The brightness of the volcano increases and decreases in a cycle that appears to correlate with the changing shape of Io's orbit, although more data is required to confirm this synchronization completely. Interestingly, observations indicate that bright eruptions are more prevalent on the posterior hemisphere of Io, the side of the Moon that faces backward in its orbit around Jupiter. The reason for this specific distribution is currently explained by models of tidal heating, yet it adds another layer to the complexity of the Moon. Furthermore, the global mapping of volcano locations does not perfectly align with any single major heating model, suggesting that the interior structure of Io is more intricate than our initial simulations predicted. As we continue to analyze the data, we find that Io poses as many questions as it answers. The comparison between Earth and Io highlights the extreme nature of the Jovian system. On Earth, a large volcanic eruption can impact the global climate, often injecting ash into the atmosphere that leads to temporary cooling. On Io, the volcanoes do not just modify the atmosphere, they essentially create it. The Moon possesses a very thin atmosphere composed mostly of sulfur dioxide, which is sustained by the constant volcanic outgassing. A particularly powerful eruption observed in the year 2022 demonstrated the severity of this environment. The event was energetic enough to illuminate the region of space surrounding the Moon. This brings us to the broader influence of Io on its cosmic neighborhood. The consequences of this volcanic activity extend far beyond the gray and orange surface. Io ejects tons of material into space every second. While some of this material falls back to the surface, a significant portion escapes the Moon's weak gravity. Once in space, these particles, primarily sulfur and oxygen ions, become trapped by Jupiter's powerful magnetic field. They form a donut-shaped ring of charged particles around the planet, known as the Io plasma torus. This structure contributes heavily to Jupiter's magnetosphere, the vast region of space dominated by the planet's magnetic influence. As the plasma torus rotates with Jupiter, it strips electrons from the atoms, creating a powerful electrical current. These particles travel along the magnetic field lines toward Jupiter's poles. When they collide with the gases in Jupiter's upper atmosphere, they transfer energy and create intense, bright auroras that shine in ultraviolet and X-ray wavelengths. While the interaction between Io's atmosphere and Jupiter's magnetic field creates dazzling displays in the upper atmosphere, the long-term consequences of this volcanic activity on the Moon itself remain a subject of intense analysis. What is scientifically certain is that the surface of Io is in a state of constant rejuvenation. The relentless deposition of lava and ash buries the old crust, erasing geological history and creating a dynamic environment that challenges our standard models of habitability. Io is, by all measurements, a world of extremes. Its surface presents a landscape that appears hostile to biology as we understand it. The average surface temperature drops to -202 degrees Fahrenheit, a chilling cold caused by the lack of a substantial atmosphere to trap heat. Yet, in stark contrast, the volcanic hotspots scattered across the terrain can spike to a scorching 2,900 degrees Fahrenheit. This immense thermal variance creates a chaotic environment where the ground is either frozen solid or molten liquid. It is difficult to conceptualize life surviving in such a volatile setting. However, biology is often more resilient than our initial assumptions suggest. On Earth, we observe organisms known as extremophiles that thrive in conditions previously thought to be sterile. We find life in the crushing, high-pressure depths of the ocean trenches and in the boiling, acidic springs of Yellowstone National Park. These organisms do not rely on sunlight. Instead, they utilize chemical energy from the Earth's interior. This biological resilience leads astrobiologists, such as Dirk Schulze-Markuch, to propose that if life exists on Io, it has likely retreated underground. Despite the radiation and temperature extremes on the surface, the subsurface environment could theoretically act as a sanctuary. The layers of rock and sulfur would shield potential organisms from the lethal charged particles of Jupiter's radiation belts, while the internal tidal heating could provide a stable source of warmth and perhaps pockets of liquid fluids necessary for biological functions. A primary candidate for such a habitat would be lava tubes. These are natural subterranean channels formed when a flowing river of lava cools on the surface, creating a hard crust while the molten rock continues to flow beneath. When the eruption ceases and the lava drains away, a hollow tunnel remains. Given the intensity of volcanism on Io, these structures should be geologically common. On Earth, lava tubes are known to harbor microbial life regardless of the external climate. They provide a stable microenvironment protected from wind, radiation, and temperature swings. If similar structures exist on Io, they could serve as the most plausible location for biological activity. However, if life has evolved in these dark corridors, it would likely be fundamentally different from the carbon-based, water-dependent life we see on Earth. It would be an evolution driven by the unique chemistry of the Moon. In this sulfur-rich environment, organisms might not use water as a biological solvent. Instead, they could potentially utilize hydrogen sulfide. While hydrogen sulfide is a toxic gas to humans, in the specific pressure and temperature conditions of Io's subsurface, it could exist in a liquid state. It has the ability to dissolve organic compounds, much like water does on Earth. Furthermore, instead of using oxygen for respiration or sunlight for photosynthesis, these theoretical life forms could derive energy from breaking down sulfur compounds. This suggests a biosphere that is entirely alien, yet chemically consistent with the environment it inhabits. While the existence of life on Io remains strictly in the realm of speculation, the possibility cannot be scientifically ruled out without direct investigation. To move from speculation to evidence, we rely on advanced observation. Our understanding of Io's internal mechanics has improved dramatically due to the continuous stream of data from robotic explorers. The NASA Juno spacecraft, which has been in orbit around Jupiter since the year 2016, has provided the most detailed views of this moon to date. A critical instrument in this endeavor is Juno's Jovian Infrared Auroral Mapper, known by the acronym JIRAM, or JIRAM. This instrument was designed to study the upper layers of Jupiter's atmosphere, but it has proven invaluable for monitoring Io. Because JIRAM operates in the infrared spectrum, specifically at a wavelength of about 5 microns, it detects heat rather than visible light. This allows scientists to see through the shadows and identify the thermal signature of volcanoes, even on the night side of the moon. Through repeated passes, JIRAM has allowed researchers to map the distribution of heat across the satellite. By observing the moon over time, scientists can track the variability of the volcanoes, how frequently they erupt, how the intensity of the heat changes, and whether the eruptions occur in clusters or as isolated events. This data is vital for constructing a comprehensive model of Io's mass and energy flow. Understanding how much heat is coming out of Io tells us how much tidal energy is being generated inside it. This, in turn, helps refine our understanding of orbital dynamics and the evolution of the entire Jovian system. The future of this exploration holds promising developments. The trajectory of the Juno spacecraft is being adjusted to bring it closer to the moon. Upcoming maneuvers will result in twin flyby encounters, where the probe will pass just 900 miles above Io's surface. In astronomical terms, this is a remarkably close approach. Such proximity will allow the onboard cameras and sensors to resolve surface features with unprecedented clarity, potentially revealing the topography of the lava lakes and the height of the volcanic plumes in high definition. In parallel with Juno, the European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, is en route to the system, expected to arrive by the year 2031. JUICE is primarily tasked with studying the ocean-bearing moons Europa, Ganymede, and Callisto. However, its broad suite of instruments will contribute significantly to our knowledge of Io as well. Since Io is the primary source of plasma in Jupiter's magnetosphere, understanding Io is essential for understanding the environment of the icy moons. The data collected will help scientists answer fundamental questions about the formation of the planetary bodies and the cosmic forces that dictate their evolution. Looking further ahead, there is a proposed mission dedicated specifically to this volcanic world, the Io Volcano Observer, or IVO. This mission is designed to investigate tidal heating as a fundamental planetary process. The scientific objectives are precise: to determine exactly how and where heat is generated inside the moon, how that heat moves to the surface, and how the internal structure of Io has changed over millions of years. These findings would have direct implications for our understanding of other worlds. If we can solve the thermal history of Io, we gain better insight into the subsurface oceans of Europa and Enceladus, which are also powered by tidal heating. Furthermore, Io serves as a planet-sized natural laboratory. By studying it, we can better understand the mechanics of exoplanets in other star systems that undergo similar gravitational stresses. The proposed baseline for the IVO mission involves a launch that would see the spacecraft reach Jupiter in August of the year 2033. To achieve this, the mission planners have designed a trajectory known as a MEGA, or Mars-Earth Gravity Assist. This complex navigation technique involves flying the spacecraft past Mars and Earth to use their gravitational fields as a slingshot, boosting the probe's speed and adjusting its path without consuming excessive fuel. During its core mission, IVO would approach Io 9 times over a period of 4 years. Exploring this region is not without significant logistical challenges. The environment around Io is one of the most hazardous in the solar system due to the intense radiation trapped by Jupiter's magnetic field. This radiation can fry electronics and degrade sensors. However, the engineering challenge is balanced by the potential for discovery. Every obstacle overcome pushes the boundaries of our technical capabilities and deepens our knowledge of the universe. As we consider the extreme nature of these distant satellites, it provides a renewed perspective on the celestial body most familiar to us. In the vast expanse of space, it hangs in our sky as a silent guardian and a constant companion. The moon, our moon, has been a fixed point of reference for humanity for thousands of years. It has served as a calendar for ancient civilizations, a guide for navigators crossing the oceans, and a subject of study for early astronomers. We have observed its phases, mapped its craters, and, in the 20th century, physically walked upon its surface and returned samples to Earth. Despite this long relationship, the moon continues to hold secrets that compel us to return. It is not merely a dusty relic of the early solar system. It is a complex geological body with a mysterious history. We now stand at the threshold of a new era of lunar exploration. The Artemis missions represent a bold venture that promises to extend human presence further than ever before. Unlike the brief sorties of the Apollo era, this new phase of exploration aims to reveal truths that have been preserved in the lunar regolith for billions of years. Recent analyses have already begun to shift our understanding. Did you know that deep beneath the cratered gray surface, the moon possesses a solid iron core, similar in some respects to Earth's? Furthermore, we have confirmed that water ice is hidden in the permanent shadows of craters at the lunar poles regions that have not seen sunlight for eons. These are not just geological footnotes, they are resources and clues to the history of the Earth-Moon system. From stunningly detailed images revealing the true mineral colors of the surface to groundbreaking geological discoveries regarding its interior structure, we are learning more about our celestial neighbor than ever before. Let's dive into the fascinating world of lunar discoveries. To fully appreciate the significance of these modern discoveries, we must first look backward to the history of observation. The moon has been a constant variable in the human experience since before recorded history. For millennia, it was the primary source of light in the night sky, serving as a reliable timekeeper for agricultural societies. Ancient civilizations meticulously tracked its phases, creating the first lunar calendars, systems of time measurement that remain continuously in use within various cultures today. However, for most of human history, the moon was understood through the lens of mythology rather than geology. This perspective shifted fundamentally in the 17th century with the invention of the telescope, when astronomers like Galileo Galilei trained their optical instruments on the lunar disk. They did not see a perfect, smooth celestial sphere as predicted by ancient philosophy. Instead, they observed a rugged world of mountains, craters, and vast, dark plains. They termed these dark areas maria, or seas, mistakenly believing they were bodies of water, while we now know these are dry plains of basalt. The realization that the moon was a physical place with topography was a turning point in science. This observational science accelerated dramatically in the 20th century, driven by the geopolitical pressures of the space race. The launch of Sputnik by the Soviet Union in the year 1957 initiated a period of rapid technological advancement, culminating in NASA's Apollo program. In July of 1969, the Apollo 11 mission achieved a definitive milestone when Neil Armstrong and Buzz Aldrin became the first human beings to physically stand upon the lunar regolith. This event was not merely symbolic, it was a massive data acquisition exercise. The Apollo missions returned hundreds of pounds of rock and soil samples to Earth. These samples revolutionized planetary science, proving that the moon was not a primordial object captured by Earth's gravity, but rather a body that shared a common and violent history with our planet. Since the conclusion of the Apollo era, the study of the moon has transitioned into a global endeavor. Robotic missions from various nations have mapped the topography in high resolution, analyzed the thin exosphere, and detected chemical signatures of water. This accumulated knowledge has laid the foundation for the Artemis program. Named after the twin sister of Apollo in Greek mythology, Artemis represents the 21st century approach to lunar exploration. The inaugural mission, Artemis 1, was a critical uncrewed test flight designed to validate the safety of the Orion spacecraft. It was not simply a loop around the moon. It was a stress test of engineering limits. During its voyage, the Orion capsule flew farther from Earth than any human-rated spacecraft had ever traveled, entering a distant retrograde orbit that took it 40,000 miles beyond the moon itself. The mission objectives focused on system durability in the deep space environment, particularly regarding radiation shielding and communication navigation. The spacecraft's cameras captured images of the lunar surface that served both public engagement and technical verification purposes. These high-definition views allowed engineers to visually inspect the spacecraft's structural integrity mid-flight. The conclusion of the mission was equally critical. Orion returned to Earth at a speed of nearly 25,000 miles per hour, often simplified to 20,000 in general reports, but specifically fast enough to generate immense friction. The heat shield had to withstand temperatures of 5,000 degrees Fahrenheit upon re-entry. The successful splashdown and recovery validated the architecture for future crewed missions. This success was the result of decades of engineering refinement, aiming to return humans to the lunar surface and eventually establish the logistical framework for a journey to Mars. Scientific interest in the moon extends far beyond its use as a launching pad. It is a geological archive of the early solar system. Unlike Earth, where tectonic activity and erosion constantly recycle the crust, the moon's surface is static. It preserves the history of cosmic bombardment. The rugged landscape of mountains and impact craters tells the story of the chaotic period known as the Late Heavy Bombardment. Furthermore, the samples returned by astronauts confirmed that the dark plains, or maria, are composed of basalt, a dense, iron-rich volcanic rock formed from rapidly cooling lava. This confirms that the Moon was once a geologically active world with flowing magma. One of the most significant recent breakthroughs concerns the interior structure of the Moon. For decades, the nature of the lunar core was a subject of theoretical debate. Recent reanalysis of data has provided a clearer picture. Much like the Earth, the Moon is differentiated into layers: a crust, a mineral-rich mantle, and a core. However, there is a distinct difference. While Earth possesses a liquid outer core that generates our strong magnetic field, the Moon's core is believed to be largely solid. This conclusion is derived from seismic data originally collected by the Apollo missions. Astronauts placed seismometers on the surface that operated for years, recording lunar tremors or moonquakes. By measuring how these vibrations traveled through the Moon's interior, scientists could effectively X-ray the body. The data indicates the presence of a solid iron inner core. The existence of this solid core is crucial for reconstructing the thermal history of the Moon. It suggests that billions of years ago, the core was molten and likely generated a global magnetic field, which would have protected the ancient surface from solar radiation, much like Earth's field does today. As this iron core cooled and solidified over eons, the Moon physically contracted. This shrinking process forced the crust to buckle, creating cliffs and ridges that we observe today. Furthermore, the density and composition of the core support the giant impact hypothesis. This is the leading theory that the Moon formed from the debris, resulting from a cataclysmic collision between a young Earth and a Mars-sized protoplanet named Theia. This violent event would have created a molten ocean of rock that slowly coalesced and cooled to form the satellite we know today. As we continue to analyze these geological layers, we find that every stratum from the crust to the core holds information about planetary evolution. Among these discoveries, the presence of volatile compounds has shifted our strategy for exploration. Water is the essential definition of habitability. For the majority of modern astronomy, the Moon was considered a bone-dry, airless rock, completely devoid of moisture. Recent robotic missions have overturned this assumption. The key lies in the Moon's axial tilt. Because the Moon is tilted only slightly relative to the Sun, there are deep craters near the north and south poles that have never seen sunlight. These are known as permanently shadowed regions. In these traps, temperatures can plummet to -400 to 18 degrees Fahrenheit. At this thermal extreme, water molecules cannot sublimate into a gas. They remain trapped as hard ice for billions of years. Evidence for this ice has been accumulating from multiple sources. NASA's Lunar Reconnaissance Orbiter, or LRO, has been orbiting the Moon since 2009, using laser altimeters and temperature sensors to map these cold traps in detail. The data from LRO strongly suggested the presence of hydrogen. To confirm this, NASA launched the LCROSS mission, the Lunar Crater Observation and Sensing Satellite. This mission involved a kinetic experiment where a spent rocket stage was deliberately crashed into a crater near the lunar South Pole. The impact excavated tons of material, creating a plume of debris that rose into the sunlight. Instruments analyzing the light from this plume detected the definitive chemical signature of water, ice, and vapor. More recently, research has moved from simple detection to detailed mapping. Using data from SOFIA, the Stratospheric Observatory for Infrared Astronomy, which is essentially a telescope mounted on a Boeing 747 scientists have been able to distinguish water molecules from other hydroxyl compounds. A recent study utilizing this data produced a map of water distribution near the South Pole. The findings reveal that water is not a uniform layer. It is patchy, concentrated in specific craters and rough terrains. The origin of this water is still an open question. It may be ancient water released from the moon's interior during volcanic eruptions, or it may have been delivered externally by comets, asteroids, and interactions with the solar wind. There is also the question of whether this water migrates across the surface during the lunar day. This mapping effort is not purely academic. It is a strategic necessity for future operations. Knowing the precise location of water ice is the first step in resource utilization. For human explorers, water is heavy and expensive to launch from Earth. Finding it on the moon changes the logistics of spaceflight. It can be purified for drinking and used for agriculture in orbital habitats. More critically, water is chemically composed of hydrogen and oxygen. By applying electricity to water, these two elements can be separated. Liquid hydrogen and liquid oxygen are the primary components of high-efficiency rocket fuel. This implies that the lunar poles could effectively serve as mining sites and processing plants. If we can harvest and process this ice, the moon becomes a refueling station in space, allowing spacecraft to top off their tanks in orbit before departing for destinations farther out in the solar system, such as Mars. While the search for water ice captures the headlines regarding resource utilization, another assumption about the moon often goes unexamined. When we visualize the lunar environment, we typically imagine a complete vacuum, a barren, airless world where the sky is instantly black. However, technically speaking, the moon does possess an atmosphere. It is incredibly thin and rarefied, but it exists and is currently the subject of intense scientific research. In planetary science, this type of atmosphere is classified as a surface-bounded exosphere. It is the most tenuous type of atmosphere possible. To understand the difference, consider the air on Earth. Molecules are constantly colliding with one another, creating pressure. On the moon, the gas is so sparse that individual molecules rarely, if ever, collide. Instead, they follow ballistic trajectories launching from the surface, arcing through the void like tiny rockets, and falling back down without hitting anything else. The composition of this exosphere is a mix of helium, neon, and argon, along with traces of other heavier elements. These gases are not permanent residents. They are constantly lost to space and replenished. The primary source of replenishment is a process known as degassing, where radioactive decay within the moon's interior releases gas that seeps up through the soil. To better understand this delicate environment, NASA launched the Lunar Atmosphere and Dust Environment Explorer, known by the acronym LADE. This mission, launched in the year 2013, was designed specifically to orbit low and sample this tenuous gas layer before it was disturbed by further human activity. LADE made detailed measurements of the exosphere's structure, but arguably its most significant finding related to dust. The spacecraft confirmed the existence of a permanent asymmetrical dust cloud hovering over the lunar surface. This is not dust blown by wind, but dust kicked up by the constant rain of micrometeorites. When these tiny particles from space strike the moon at high speeds, they eject secondary debris high into the exosphere. This creates a temporary, ever-changing veil of dust that rises and falls with the rhythm of the impactors. Understanding this dust environment is not merely an academic exercise, it is a safety requirement for future operations. Lunar dust is electrostatically charged and highly abrasive. As we prepare for sustained missions, we must account for how this dust interacts with landing gear, solar panels, and life support systems during takeoff and landing phases. Just as our understanding of the Moon's exosphere has been refined by orbital sensors, our ability to visualize the surface from Earth has undergone a similar revolution. We have moved far beyond the grainy, black and white telescopic sketches of the 17th century. In this current era of advanced astronomy, digital imaging technology allows us to capture the stark landscape of the Moon with a level of clarity that rivals orbital photography. We have witnessed a progression from the earliest chemical film plates to the ultra-high resolution sensors of modern observatories. However, some of the most striking advances are coming from the application of computational photography. A prime example of this technological achievement was produced recently by astrophotographers Andrew McCarthy and Connor Mathernay. They created an image of the Moon that went viral in the scientific community, not for its artistic merit alone, but for its technical precision. This portrait of the Moon is not a single snapshot. It is a composite mosaic constructed from more than 200,000 individual images captured over the course of a single evening. The technique used here is known as stacking. When photographing space from Earth, the turbulence of our own atmosphere causes the image to shimmer and blur, similar to looking at an object through heat waves rising from hot pavement. By taking thousands of photos of the same spot and using software to align them, photographers can average out the atmospheric distortion. This process drastically increases the signal-to-noise ratio, isolating the true details of the lunar surface from the visual noise of Earth's air. The final result of this labor-intensive process is a spectacular 174 megapixel masterpiece. At this resolution, the image reveals the Moon with unprecedented texture. Every crater, rim, mountain peak, and rill is sharply defined. Perhaps more importantly, the image utilizes color enhancement to reveal the geological reality of the surface. To the naked eye, the Moon appears gray. However, the soil contains varying concentrations of minerals like titanium and iron. In the processed image, these chemical differences manifest as subtle blue and orange hues, effectively creating a geological map of the regolith. Achieving this requires not only advanced optics and clear skies, but a mastery of data processing. Merging hundreds of thousands of files requires hundreds of hours of computer time to ensure every pixel is perfectly aligned. These images serve a dual purpose. They engage the public with the beauty of the cosmos, but they also serve as independent datasets for scientists tracking changes in surface reflectivity or planning potential landing sites for future robotic probes. As we analyze these high-resolution maps, we are effectively scouting the territory for the next phase of human history. One mission currently stands as the beacon illuminating this path: Artemis II. This is the designated successor to the Apollo program and represents the next logical step in our journey toward a multi-planetary existence. Artemis II, a core component of NASA's broader exploration strategy, will mark the first time in the 21st century that humans will venture beyond low Earth orbit. It is a mission designed to take a crew of astronauts on a trajectory around the Moon and back, validating the systems required for deep space survival. The crew selected for Artemis II represents a significant shift in the demographics of space exploration. It is a diverse and highly specialized team, including the first woman and the first person of color to participate in a lunar mission, reflecting a broader inclusion of humanity than was seen in the 1960s. The mission will be commanded by NASA astronaut Reed Wiseman, with Victor Glover serving as the pilot. They are joined by mission specialists Christina Hammock-Cock, who holds the record for the longest single spaceflight by a woman, and Jeremy Hansen from the Canadian Space Agency. The inclusion of a Canadian astronaut underscores the international nature of this new era. Unlike the space race, which was a competition, the Artemis program is a coalition. The operational goals of Artemis II are rigorous. This will be a multi-day mission focused on testing the critical life support and navigation systems of the Orion spacecraft and the Space Launch System rocket. Before we can commit to landing on the surface, we must be certain that the vehicle can sustain human life in the high radiation environment of deep space. This mission will pave the way for Artemis III, which intends to put boots on the ground near the lunar South Pole. But Artemis II is more than a test flight. It is the revival of the spirit of human exploration, taking us physically beyond the protection of Earth's magnetic field for the first time in 5 decades. It is important to understand that Artemis II is just the beginning of a sustained architecture. The long-term objective is not a series of flags and footprints missions, but the establishment of a permanent human presence. The moon is viewed effectively as a proving ground, a sandbox where we can test the technologies and strategies needed to survive on other worlds. We need to learn how to live off the land, a concept known as in situ resource utilization. If we can master the extraction of water, oxygen, and building materials from the lunar soil, we can apply those same techniques to Mars. In this context, the moon is more than a destination. It is a gateway. It is the logistical stepping stone that makes the rest of the solar system accessible. As we stand on the threshold of this new era, looking toward Mars and the distant worlds awaiting our arrival, we recognize that the road to the stars begins with our closest neighbor. In the grand theater of the cosmos, few relationships are as physically coupled and intricate as the bond between the Earth and the Moon. This partnership, which emerged from a violent collision more than 4.5 billion years ago, has dictated the geological and biological fate of our planet. The Moon is our constant satellite, orbiting at an average distance of about 238,855 miles. While this distance may seem vast, in astronomical terms, it is intimate. The Moon is the 5th largest satellite in the solar system, but when compared to the size of the planet it orbits, it is exceptionally large. This unique ratio creates a system that functions almost like a double planet. As the Moon revolves around the Earth, the changing geometry of the Sun, Earth, and Moon creates the cycle of phases that has marked the passage of time for human civilization. When the alignment is precise and the Moon passes into the Earth's shadow, we witness a lunar eclipse, a phenomenon that turns the lunar surface a deep, blood-red color due to sunlight filtering through Earth's atmosphere. Beyond these visual spectacles, the Moon exerts a tangible physical force on our planet through gravity. This gravitational pull is the engine behind Earth's tides. As the Moon orbits, its gravity tugs on Earth's oceans, creating a bulge of water on the side facing the satellite. Simultaneously, because the Earth is also being pulled toward the Moon, a second bulge creates itself on the opposite side due to inertia. This results in the rhythmic rise and fall of 2 high tides and 2 low tides every day, a cycle that drives ocean currents and influences marine ecosystems globally. Furthermore, the Moon acts as a physical shield. The cratered surface of the Moon is a testament to billions of years of bombardment. By absorbing impacts from asteroids and comets, the Moon has, on statistically significant occasions, spared Earth from catastrophic collisions. However, the most profound contribution of the satellite is its stabilizing influence. The gravitational interaction between the 2 bodies acts like a cosmic anchor. Without the Moon, the tilt of Earth's axis, currently stable at about 23.5 degrees, would wobble chaotically over millions of years, similar to the behavior seen on Mars. This wobble would cause extreme and unpredictable climate swings, potentially preventing the development of complex life. The Moon has maintained our climate stability for eons, providing the steady conditions necessary for evolution to take hold. As we continue to explore the Moon, both through telescopic observation from Earth and with direct contact missions like Artemis, we do not just learn about our celestial neighbor. We also gain insight into our planet, its history, and its place in space. While our exploration of the Moon provides crucial insights into the formation of our local solar system, human curiosity extends far beyond our immediate neighborhood. We are driven to answer one of the oldest and most profound questions humanity has ever posed. Are we alone in the universe? For generations, this question remained philosophical, but recent technological advancements have shifted it into the realm of observational science. The James Webb Space Telescope may have just brought us one step closer to a revolutionary discovery. This brings our attention to K2-18b, a distant exoplanet that has suddenly found itself at the forefront of astrobiological research. The reason for this intense focus lies in the data returned by the telescope. James Webb has detected something unusual in the planet's atmosphere, chemical signatures that could potentially signal the existence of biological processes. The detection of molecules such as water vapor, methane, and specifically the rare compound dimethyl sulfide is significant. These are not merely random collections of atoms. In the context of Earth, they can serve as biosignatures, clues that suggest life in some form is modifying the environment. To understand the gravity of this finding, we must first understand the instrument that made it possible. James Webb is often described as the new guardian of the galaxy, but more accurately, it is the most sophisticated infrared observatory ever constructed. It was designed specifically to peer into the unknown and clarify our understanding of planetary formation and potentially life itself. So, let us venture across the galaxy to analyze the mysterious world of K2-18b as we look deeper into space, searching for answers that have puzzled us for eons. We rely entirely on the sensory capabilities of our machines. The James Webb Space Telescope, often abbreviated as JWST, represents a quantum leap in this capability. For decades, the Hubble Space Telescope served as our primary window to the universe. Hubble produced images in visible light that delighted the public and enlightened astronomers, but it operated with physical limitations. Visible light is easily blocked by cosmic dust and gas. To see the hidden details of exoplanets and star-forming regions, we needed to look in a different part of the spectrum, the infrared. This is where James Webb pushes the boundaries of what is possible. One of the most innovative engineering features of the JWST is its thermal control system, specifically its sunshield. This is not an ordinary shade. It is a masterpiece of thermal engineering the size of a tennis court. It consists of 5 separate layers of a specialized material called kapton, each thinner than a human hair and coated with aluminum and doped silicon. This shield blocks the intense heat from the sun, the Earth, and the Moon. This extreme cooling is critical because the telescope is designed to detect infrared light. Infrared radiation is essentially heat. If the telescope were warm, its own heat would blind its senses, much like trying to see a candle while standing next to a spotlight. By keeping the instruments at incredibly low temperatures, -370 degrees Fahrenheit or lower, the telescope achieves the sensitivity required to detect the faint heat signals emitted by distant celestial bodies. This infrared capability is crucial for studying exoplanets like K2-18b. Unlike visible light, which is often scattered or absorbed by interstellar dust, Infrared waves pass through these obstacles with greater ease, providing us with clearer and more detailed data. This ability to conduct deep infrared surveys is not just a technical achievement, it is a revolution in how we characterize distant worlds. So, what exactly have we found when turning this powerful gaze toward K2-18b? This planet is located approximately 124 light-years away from Earth in the constellation Leo. In the vast scale of the galaxy, this is relatively close, yet it is a world entirely distinct from our own. You may be familiar with the term Goldilocks zone or the habitable zone. This defines the specific distance from a star where temperatures are just right, neither too hot nor too cold for liquid water to exist on a planet's surface. K2-18b orbits its parent star, a red dwarf named K2-18, precisely within this habitable region. However, simply being in this zone does not guarantee habitability. What sets K2-18b apart is its classification. It is not a gas giant like Jupiter, nor is it a small, rocky world exactly like Earth. It belongs to a theoretical class of planets known as Hycean worlds. The term Hycean is a combination of hydrogen and ocean. These worlds are characterized by massive, deep oceans covering the entire surface, situated beneath a thick, hydrogen-rich atmosphere. Hycean worlds represent a new frontier in the search for extraterrestrial life, because they challenge our Earth-centric view. Their massive oceans and thick atmospheres allow for a wider range of stable temperatures, potentially expanding the habitable zone significantly compared to rocky planets. These global oceans could offer conditions similar to the hydrothermal vent systems found in Earth's deep oceans, which are known to support diverse and robust ecosystems. Recent observations by the James Webb Space Telescope have revealed the specific chemical makeup of K2-18b's atmosphere, and the results are intriguing. The data indicates a complex cocktail of elements, including water vapor, methane, and carbon dioxide. However, the most provocative finding is the potential trace of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by life. It is released by phytoplankton in marine environments. The presence of this molecule, alongside methane and carbon dioxide, creates a chemical profile that is difficult to explain through geological processes alone. This discovery has caused a wave of excitement and cautious optimism within the scientific community. Researchers are currently analyzing the data with great scrutiny, pondering the implications for astrobiology. If confirmed, this would suggest that life can exist in environments vastly different from the rocky, nitrogen-dominated world we inhabit. Could this Hycean world, with its crushing atmospheric pressure and global sea, be the key to unlocking the mystery of biology in the cosmos? To answer this, we must understand the difficulty of the observation. Studying the atmosphere of a planet more than 100 light-years away is a task of immense precision. Scientists use a technique called transit spectroscopy. When K2-18b passes in front of its parent star from our perspective, a tiny fraction of the star's light filters through the planet's atmosphere on its way to Earth. As this light passes through the gas layers, different molecules in the atmosphere absorb specific wavelengths of light. This absorption leaves dark lines in the spectrum, creating a unique chemical fingerprint or barcode. By decoding this barcode, astronomers can determine exactly what gases are present. The infrared capabilities of the James Webb Space Telescope were essential for this analysis. Specifically, the Mid-Infrared Instrument, or MIRI, and the near-infrared imager and slitless spectrograph allowed for an extended range of wavelengths to be captured. This sensitivity allowed the detection of molecules that were previously elusive to older telescopes. The chemical balance found is particularly telling. The presence of methane and carbon dioxide, combined with a distinct lack of ammonia, is consistent with the chemical signature of a water ocean residing under a hydrogen atmosphere. This validates the High-Sheehan hypothesis. On Earth, methane is often a byproduct of biological activity, produced by bacteria in wetlands, oceans, or the digestive systems of animals. Its abundance on K2-18b, in a hydrogen-rich environment, opens up the possibility of metabolic processes we have never directly encountered. This suggests that, underneath the thick clouds, a massive subsurface ocean exists. This opens exciting questions about the interaction between the atmosphere and the ocean. How do gases exchange between the water and the air? How do these dynamics affect the overall temperature and stability of the planet? The atmosphere may indeed be the primary indicator of a habitable environment below. When we think of life, we often default to imagining Earth-like forests or shallow seas. But in reality, life is incredibly adaptable and exists in environments that humans would find instantly lethal. To understand what might live on K2-18b, we look to extremophiles on Earth organisms that thrive in extreme conditions, deep in Earth's oceans, far beyond the reach of sunlight. Hydrothermal vents spew superheated, mineral-rich water into the freezing darkness. In these toxic, high-pressure environments, life does not just survive, it flourishes. Extremophiles, such as thermophiles, heat lovers, and acidophiles, acid lovers, build entire ecosystems based not on photosynthesis, but on chemosynthesis deriving energy from chemicals rather than the sun. These organisms challenge our traditional understanding of biological limits. If life can thrive in the scalding, crushing depths of Earth's oceans, could similar life forms exist in the global ocean of a High-Sheehan world? The hydrogen-rich atmosphere of K2-18b offers unique metabolic opportunities. On Earth, certain microbes, known as methanogens, produce methane as a waste product in oxygen-free environments. If the methane detected in the atmosphere of K2-18b is indeed produced biologically, we may be looking at a biosphere dominated by hydrogen-loving extremophiles. This study of extremophiles expands the definition of the habitable zone. We see life in the highly acidic Rio Tinto River in Spain, and we find dormant bacteria in the permafrost of the Siberian tundra. Life on Earth demonstrates a tenacious ability to occupy every available niche. This biological diversity encourages us to reconsider the ecological limits of the universe. We can no longer limit our search to Earth twins. The potential for a warm, liquid ocean protected by a heavy hydrogen atmosphere makes K2-18b an attractive target for future study. It represents a laboratory for testing our theories about where life can emerge. Perhaps this distant world has developed its own version of biology, perfectly adapted to such high-pressure, hydrogen-rich conditions, and in doing so, is effectively making a name for itself. If biological organisms, specifically extremophiles, have indeed established a foothold on K2-18b, we must then consider their evolutionary trajectory. On Earth, the fossil record indicates that life began as simple, single-celled entities. Over billions of years, driven by environmental pressures and genetic variation, these simple forms radiated into complex, multicellular structures. A fundamental question in astrobiology is whether this progression is a universal constant. Given sufficient time and a stable environment, does simple life inevitably climb the ladder of complexity? Or is Earth an outlier? The answer may lie in the chemical byproducts these organisms leave behind. This brings us to the most provocative aspect of the current research surrounding K2-18b, the potential detection of dimethyl sulfide, or DMS. On our planet, this organic molecule is not a product of geology, it is a product of biology. It is primarily synthesized by marine phytoplankton and algae in the upper layers of the ocean. In the Earth's ecosystem, DMS plays a critical role in the global climate system. When it escapes the ocean and enters the atmosphere, it oxidizes and aids in cloud formation by providing nuclei for water droplets to condense around. If this same mechanism is operating on K2-18b, the presence of DMS could be the first tangible evidence of an alien biosphere functioning on a planetary scale. It would suggest that life there is not just present, but abundant enough to alter the chemistry of the entire atmosphere. However, the detection of DMS by the James Webb Space Telescope is currently at the limit of the instrument's signal-to-noise ratio. The mid-infrared instrument, or MIRI, is technically capable of resolving these spectral lines, but distinguishing a faint signal from background noise requires rigorous statistical analysis. The scientific community has reacted to this data with a necessary balance of excitement and skepticism. This caution is a safety mechanism within the scientific method. While some researchers view the data as a strong candidate for a biosignature, others argue that we have not yet ruled out all abiotic or non-biological explanations. Complex photochemistry in a hydrogen-rich atmosphere might create compounds that mimic DMS without the need for life. This debate highlights the inherent difficulty of interpreting data from 124 light-years away. Historically, major astronomical shifts have always faced resistance and rigorous testing. When Galileo Galilei first reported the existence of moons orbiting Jupiter, contradicting the geocentric model, his findings were met with rejection until they could be independently verified. Similarly, the discovery of the first exoplanet orbiting a sun-like star in 1995 was initially viewed with extreme caution. These historical precedents serve as a reminder that skepticism is not a hindrance, it is the filter that ensures accuracy. The search for extraterrestrial life will likely not depend on a single smoking gun molecule. Instead, scientists are looking for a disequilibrium, a combination of gases that should not exist together unless something is actively maintaining them. For instance, finding methane and water vapor alongside DMS creates a more compelling case than finding any of them in isolation. This debate will likely continue until the next generation of observational hardware comes online. The James Webb Space Telescope has revolutionized our view, but it is merely one step in a continuous technological progression. To resolve these ambiguities, we look toward the future ground-based and orbital observatories. The Extremely Large Telescope, or ELT, currently under construction and scheduled for completion around the year 2025, promises to be a decisive instrument. Located in the Atacama Desert of Chile, the ELT will feature a main mirror with a diameter of roughly 128 feet. This massive collecting area will make it the largest visible and near-infrared telescope in the world, capable of gathering significantly more light than any space telescope. Its unprecedented sensitivity could allow astronomers to confirm or refute the tentative biosignatures detected by Webb. Looking further ahead, we anticipate the Large UV Optical Infrared Surveyor, known as LUVOIR. This proposed mission represents a massive orbital observatory designed to operate across a wide range of wavelengths. Unlike current telescopes that mostly infer the presence of planets through shadows and gravity, LUVOIR is designed with the capability to potentially obtain direct images of Earth-like exoplanets, turning them from points of data into visible worlds. As our targets move further away, we must also consider the limitations of travel. While observation is our current tool, propulsion technology is the key to eventual contact. Advanced concepts such as ion propulsion, which uses electric fields to accelerate ions for long-duration thrust, and theoretical antimatter propulsion, which releases immense energy from matter-antimatter annihilation, could eventually reduce travel times from millennia to durations manageable within a human lifetime. We have previously analyzed the physics and immense challenges of interstellar travel in prior documentation. As we stand on the threshold of potentially validating the existence of life elsewhere, it is worth pausing to consider the philosophical weight of such a finding. If we confirm that K218b is inhabited, it reframes our understanding of existence. A significant variable in this equation is the nature of the host star. K218 is a red dwarf. These stars are smaller and dimmer than our Sun, but they are also far more numerous and incredibly long-lived. A red dwarf can burn steadily for trillions of years, providing a stable energy source for far longer than the current age of the universe. If these stars are indeed cradles of life, then the universe may be teeming with biological diversity. The discovery of extraterrestrial phytoplankton, or their functional equivalent, would imply that the building blocks of life are universal, arising wherever physics and chemistry permit. However, we do not always need to look to distant stars to find ocean worlds. Sometimes, the most enigmatic environments are hidden in the dark corners of our own solar system. Leaving the light of K218, we journey outward to the domain of the ice giants. Here, in the veiled depths of the solar system, lies an object that defies standard planetary formation models: Neptune's elusive moon, Triton. Buried in darkness, this seemingly frozen satellite conceals features that challenge our understanding of geology and cryogenics. Unlike the other major satellites in the solar system, which orbit their planets in an orderly fashion, Triton behaves like a rogue object. It orbits Neptune in a retrograde direction, meaning it moves opposite to the planet's rotation. This is highly unusual for a moon of its size and suggests a violent and chaotic origin. While its surface temperature hovers near absolute zero, making it one of the coldest places we have ever observed, the moon is geologically alive. Its surface is surprisingly young, showing few impact craters, which indicates that it is being constantly resurfaced. We have observed geysers of cryolava, likely a slurry of ammonia and water erupting from the interior, revealing an active, otherworldly dynamism. But the most compelling feature lies beneath the ice. Scientific models suggest that a dense layer of ice may be shielding a global subsurface ocean, a liquid realm where life could theoretically exist in the total absence of sunlight. To understand Triton, we must first understand its host. Neptune is a blue, icy giant, whipped by supersonic winds that reach speeds faster than any other planet. It is one of the most distant outposts of our system, excluding Pluto. It is the only major planet that is completely invisible to the naked eye from Earth due to its extreme distance and dimness. Orbiting this windy giant are 14 known moons, but Triton dominates the system. This strange, icy world was discovered in 1846 by the British astronomer William Lassell. Remarkably, Lassell discovered the Moon just 17 days after the planet Neptune itself was found. At the time, due to the limitations of 19th century optics, the discovery was a feat of mathematical prediction and keen observation. From the moment of its discovery, Triton attracted the attention of the scientific community because it did not fit the established patterns. In a standard planetary system, moons form from the same disk of material as the planet and orbit in the same direction. Triton breaks this rule. All other major moons in the solar system orbit in the prograde direction. Triton's retrograde orbit suggests it did not form near Neptune but was captured by the planet's gravity from elsewhere, likely the Kuiper belt. In this regard, scientists have noted a striking similarity between Triton and the famous dwarf planet Pluto. Their masses, diameters, and surface compositions, dominated by nitrogen ice, are nearly identical, suggesting they share a common lineage as icy wanderers of the outer dark. To comprehend the anomaly of Triton, we must first analyze its physical dimensions. This is not a minor piece of debris. It is a planetary scale object. The diameter of this unique satellite measures approximately 1,680 miles. To put that into perspective, it is nearly 7 times larger than Proteus, the second largest moon in the Neptune system. In fact, Triton is only slightly smaller than Earth's own moon. This substantial mass generates enough gravity to retain a tenuous atmosphere, a feature rarely seen on satellites. Spectroscopic analysis reveals that this atmosphere is composed mainly of nitrogen, with significant traces of methane. Furthermore, data indicates that the upper atmosphere possesses a fully developed ionosphere, a layer where solar radiation strips electrons from atoms, creating an electrically charged environment that is, surprisingly, more intense than what we observe on some larger bodies. These physical characteristics, a substantial atmosphere and a large diameter, are the primary indicators that Triton is not a natural moon formed in situ. Instead, it bears a striking structural resemblance to the dwarf planets of the outer solar system, specifically Pluto. The internal composition reinforces this comparison. By calculating the moon's density, scientists have determined that Triton consists of a mixture of materials, roughly 70% rock and 30% water ice. This specific ratio suggests that the moon has undergone internal differentiation. This means that at some point in its history, Triton was hot enough for the heavy rocky elements to sink to the center, while the lighter ices floated to the exterior. Consequently, we suspect that Triton possesses a structured interior similar to the terrestrial planets, a solid metallic or rocky core, surrounded by a liquid or slushy mantle, and capped by a hard crust. However, this internal heat fights against a brutal external environment. Orbiting at a distance of 2,793,000 miles from the Sun, Triton exists in a state of deep freeze. It is one of the coldest objects ever measured in the solar system by a visiting spacecraft. The average surface temperature drops to -400 degrees Fahrenheit, only roughly 60 degrees above absolute zero. The surface is coated in a layer of frozen nitrogen, which acts like a mirror. Beneath this lies a thick mantle of water ice, as hard as granite due to the extreme cold. This composition gives the moon an exceptionally high albedo, or reflectivity. Triton reflects about 70% of the sunlight that strikes it. For comparison, Earth's moon reflects only about 12%. This icy luster indicates that the surface ice is relatively fresh and clean, implying that Triton is not a dead, static world, but rather a geologically active planet disguised as a moon. The geological history of Triton is written on its skin. When planetary geologists analyze the surface, they find a distinct lack of heavy cratering. On most airless bodies, like our Moon or Mercury, the surface is pockmarked with billions of years of impact scars. Triton's outer layer, however, has relatively few impact craters. This is a telltale sign of resurfacing. It suggests that the surface we see today is geologically young, perhaps less than 100 million years old, and that some active process is erasing older craters. When we examine the terrain in detail, specifically the regions imaged by passing spacecraft, we see a chaotic landscape of large ridges and valleys with complex, intersecting patterns. This texture resembles the skin of a melon, leading scientists to formally dub it cantaloupe terrain. Alongside these textures are smooth, dark streaks deposited on the ice. If these features were formed solely by external impacts, Triton would be covered in massive basins. Since it is not, astronomers conclude that the landscape is being shaped from below. The leading hypothesis suggests that a massive, global ocean may be hidden beneath the insulating ice shell. The surface is likely being rejuvenated by a mixture of water, ammonia, and nitrogen, pushing up from the interior. But this raises a fundamental question of physics. How does liquid water make it to the surface in such a frozen environment? There are two primary mechanisms that can drive this transport. The first is catastrophic external events, such as massive meteorite impacts that punch through the crust, allowing subsurface fluids to well up. The second, and more consistent mechanism, is volcanism, specifically cryovolcanism. We observe similar nitrogen polar caps on the moon Titan, which are influenced by these cold eruptions. But on Triton, the drivers of this activity are unique. The moon is subjected to immense gravitational forces from Neptune. As Triton orbits, Neptune's gravity kneads the satellite, deforming its core and generating friction. This process, known as tidal heating, keeps the interior warm enough to maintain a liquid or slushy layer. Additionally, scientists propose a mechanism involving solar heating known as the solid-state greenhouse effect. Although the sun is distant, its radiation can penetrate the transparent surface ice. This energy is absorbed by the darker nitrogen ice and particles below, heating them up. As the pressure builds, the trapped gas eventually explodes outward through cracks in the crust, carrying dust and ice with it. These active geysers can sustain eruptions for more than a year, spewing tens of cubic kilometers of material into the thin atmosphere. These plumes distribute dark material across the surface, effectively repaving the moon. Heidi Hammel, a senior researcher at the Institute of Space Sciences, argues that sustaining such high-altitude geysers requires a robust heat source, strongly supporting the existence of a subsurface ocean. While the existence of this ocean remains unconfirmed by direct sounding, the hypothesis aligns with the observation of such a young surface. Heat from the core could be melting pockets of nitrogen ice, which then erupt. Alternatively, the cryovolcanoes might not be tapping into a global ocean, but rather localized pockets of meltwater within the crust. Regardless of the specific plumbing, Triton challenges our definitions of a dead, icy world. It raises numerous questions about its internal composition, and the only way to resolve these uncertainties is through direct exploration at the edge of the solar system. Our primary source of high-resolution data comes from a single historic encounter. The first telescope, and indeed the only robot to capture detailed images of Triton, was Voyager 2 in August of 1989. This was the grand finale of the Voyager Grand Tour. Flying over Neptune's North Pole, mission controllers deliberately bent Voyager's trajectory, using the giant planet's gravity to sling the probe toward Triton. This maneuver meant Voyager could not go on to visit Pluto, but the sacrifice was deemed necessary. Passing at a distance of roughly 25,000 miles, similar to the altitude of geostationary satellites above Earth, the probe captured the very first resolved images of Triton's surface before departing forever into the prized interstellar medium. It is thanks to this brief flyby that we possess a baseline for understanding the Moon today. The Voyager mission provided a comprehensive characterization of the satellite's mass, radius, and density. Crucially, its onboard spectrometers analyzed the thin air, establishing that the atmosphere is dominated by molecular nitrogen with a small percentage of methane. This detection was pivotal. It suggested that the satellite had the ingredients for geological activity and launched the study of cryovolcanic plume dynamics. Voyager 2 also settled a long-standing debate by proving that there were no open lakes or oceans of liquid nitrogen on the surface. Instead, it revealed a solid, frozen landscape. However, due to the speed of the flyby and the rotation of the Moon, Voyager 2 only imaged about 40% of the surface, primarily the southern hemisphere. Because Triton is tidally locked, meaning it always keeps one face pointed toward Neptune, we have effectively never seen the other side of the Moon in detail. Almost 33 years after that historic encounter, the James Webb Space Telescope turned its infrared gaze toward the Neptune system. Although observing from a much greater distance than Voyager, Webb's advanced sensors provided a new perspective. In the images returned by Webb, we see the faint, delicate rings of Neptune and its 7 smaller moons. However, Triton commands the scene. To the left of Neptune, in the image, there appears a very bright, star-like object, complete with diffraction spikes. This is not a star, it is Triton. The spikes are an optical artifact caused by the telescope's hardware, but they occur only because Triton is incredibly bright in the infrared spectrum. This outburst of brightness confirms that the surface is still coated in frozen condensed nitrogen, which reflects almost all the sunlight that reaches it. While these photographs taken over the past 30 years have advanced our knowledge, they are insufficient to build a complete geological map. We are left with significant gaps in our understanding. To confirm the existence of the ocean and understand the engine driving the geysers, dedicated orbital expeditions to Triton are required. Future mission concepts envision orbiters that can map the gravity field and use radar to penetrate the ice shell. Until then, we must rely on analyzing the Moon's most peculiar feature, its movement. Triton's unusual orbit is perhaps the most compelling clue to its history. As previously noted, Triton is one of the few major satellites in the solar system that moves in a retrograde direction. In simple terms, if you were looking down from the north pole of Neptune, the planet rotates counterclockwise, but Triton orbits clockwise. This is against the flow of traffic. In the solar system, prograde motion, moving in the same direction as the planet's rotation, is the standard for moons that formed alongside their parent planets. Retrograde orbits are incredibly rare for large bodies. They are usually found only on small, distant, irregular asteroids around Jupiter or Saturn. Furthermore, Triton's orbit is not flat. It is tilted by 23 degrees relative to Neptune's equator. In orbital mechanics, such a severe tilt and a reversal of motion are almost impossible to achieve if the Moon grew from the dust ring around the planet. Usually, such anomalies are the result of a massive collision. It is possible that an object struck Triton in the past, flipping its orbit, but this scenario is statistically unlikely to produce the stable, circular orbit we see today. It also fails to explain why Triton looks so much like Pluto. So, What is the explanation for this alien nature? The answer lies in the neighborhood. Neptune's orbit runs along the inner edge of the Kuiper Belt, a vast ring of icy debris and dwarf planets left over from the formation of the solar system. This is the realm where Pluto resides. There is another mechanism for acquiring a moon: gravitational capture. An independent object, moving through space at a specific speed and angle, can be snagged by a larger planet's gravity. Given the difficulty of modeling a scenario where Triton forms organically around Neptune, scientists have concluded that Triton was originally a dwarf planet cruising through the Kuiper Belt. At some point billions of years ago, it ventured too close to Neptune and was captured by the giant's gravity, forcing it into its peculiar, backward orbit. Current models of planetary dynamics suggest that Triton was likely not always a solitary wanderer. It is now believed that this satellite was once an object independent of Neptune, originating in the Kuiper Belt. In this past life, Triton was likely part of a binary system, a double planetary system, similar to the relationship between Pluto and its large moon, Charon. This binary configuration helps explain the mechanics of its capture. Capturing a single, fast-moving object is difficult because the object retains its kinetic energy and would simply fly past the planet. However, if a binary pair approaches Neptune, the gravitational physics changes. When this pair encountered Neptune, the immense gravitational pull of the ice giant disrupted the bond between the two small objects. One of the bodies would have been ejected from the solar system entirely, carrying away the excess energy, while Triton was decelerated enough to be snagged into a permanent orbit. This was a violent celestial exchange. Triton survived, but it was headed for a chaotic integration. While the companion planet was lost to the void, Triton was not the only victim of this event. When Triton arrived, Neptune likely already possessed a system of moons formed in situ. Today, we observe 13 other satellites orbiting Neptune, along with Triton. These can be categorized into two distinct groups: the inner regular moons and the outer irregular moons. A striking characteristic of this system is the distribution of mass. Triton is a behemoth compared to its neighbors. It comprises 99.5% of the total mass of all material orbiting Neptune. This suggests a history of destruction. When Triton entered the system with its massive gravity and retrograde motion, it acted like a wrecking ball. The migration of Triton likely scattered or destroyed Neptune's original moons. Many would have collided with Triton or the planet, while others were thrown out of orbit, leaving only small fragments behind. This chaotic history is most evident in the outer group of satellites. While the inner moons have resettled into stable paths, the outer icy moons bear the scars of Triton's arrival. The most prominent example is Nereid, Neptune's third largest moon. Nereid possesses one of the most eccentric orbits in the solar system. It follows a highly elliptical path, looping far out and then diving back in. At its closest approach, or perihelion, it comes within 884,500 miles of the planet. However, at its farthest point, or aphelion, it swings out to a staggering distance of 5,981,600 miles. This extreme elongation suggests that Nereid was likely knocked out of a normal, circular orbit by the migrating Triton. It managed to escape a fatal collision, but its path was permanently warped. While Triton currently dominates the system, its retrograde orbit dictates a gloomy future. Because it moves against the rotation of Neptune, tidal forces are working against it. The moon is gradually losing orbital energy, causing it to spiral inward toward the planet. It is slowly being reeled in, In a few million years, a short time in cosmic terms, Triton will cross a theoretical line known as the Roche limit. At this distance, Neptune's gravitational forces pulling on the Moon will exceed the forces holding the Moon together. Triton will be torn apart, crumbling into debris to form a spectacular new ring system around Neptune, potentially rivaling that of Saturn. Before that distant catastrophe occurs, Triton remains a world of immense scientific interest due to its potential habitability. Even though the surface is completely encased in ice made of condensed nitrogen and methane, the conditions below may be radically different. The hypothetical ocean existing beneath this frozen shell could be kept warm by tidal heating, and therefore, it could harbor life. On Earth, water is the non-negotiable solvent for biology. It serves as the medium for chemical reactions, transport, and the maintenance of cellular structures. If Triton possesses liquid water, it meets the first criteria for life. However, water alone is not enough. Biology requires chemical building blocks. In addition to the geysers of nitrogen gas observed by Voyager 2, the spacecraft documented another phenomenon: strange, dark plumes. These cryovolcanic eruptions reached altitudes of 5 miles, depositing dark streaks across the ice. The black color of this material is likely due to the presence of carbon-rich compounds. In the presence of ultraviolet light and radiation, methane and nitrogen can react to form complex organic molecules called tholins. Carbon is the fundamental scaffold for all known life, forming the backbone of DNA and proteins. While we cannot currently sample the ocean directly, scientists at the American Astronomical Society have modeled its potential composition based on the volatile elements found in comets, which share a similar origin to Triton. The models suggest the ocean is likely rich in ammonium, sodium, chloride, and dissolved oxygen. Ammonium acts as a powerful antifreeze, allowing water to remain liquid even at temperatures far below the freezing point of pure water. Nevertheless, Triton is an extreme environment. The temperatures are exceedingly low, making it unlikely that complex, multicellular life as we know it could function. The metabolic rates would be incredibly slow. Furthermore, while the satellite has a nitrogen atmosphere similar to Earth's, it is incredibly tenuous. The surface pressure is a fraction of Earth's, meaning it cannot retain significant heat, even with the presence of nitrogen clouds in the upper layers. Despite this, the climate on Triton is dynamic. In the year 2010, scientists using the Very Large Telescope of the European Southern Observatory discovered that Triton experiences seasons. Because of Neptune's long orbital period, seasons on Triton do not last 3 months. They last 40 years each. Currently, the southern hemisphere of Triton is in the middle of a long summer solstice. During this period, researchers from the Massachusetts Institute of Technology detected a slight but significant increase in surface temperature, rising from -392 degrees Fahrenheit to -389 degrees Fahrenheit. While a 3-degree shift may seem negligible, for a body near absolute zero, it represents a massive influx of energy. MIT professor James L. Elliott interpreted this as a sign of global warming on the Moon. As the nitrogen ice warms, it sublimates, turning directly from solid to gas. This gas joins the atmosphere, thickening it and increasing the surface pressure. This suggests that the atmosphere is transient. In the harsher autumn and winter months, as the temperature drops, the atmosphere essentially collapses, freezing out and settling onto the surface as snow. This implies that for half of its year, Triton may have no atmosphere at all, only for it to be resurrected in the spring. This cycle does not exclude the possibility of primitive life, but it imposes severe constraints on surface stability. To definitively answer whether Triton is a home for life, remote observation is insufficient. The images from Voyager and James Webb, while spectacular, are only scratching the surface. Triton remains one of the most intriguing, yet underexplored objects in the solar system. The desire to return is strong. A mission concept named Trident was proposed to NASA, designed to launch in the mid-2020s and arrive in 1938. This mission would have conducted a 13-day flyby, mapping the remaining 60% of the surface that Voyager missed, and using magnetometers to confirm the existence of the subsurface ocean. Unfortunately, in the year 2021, Trident was not selected for funding. NASA opted instead to fund 2 missions to Venus, Da Vinci Plus and Veritas. However, the scientific case for Triton remains solid. China is currently evaluating a nuclear-powered mission to Neptune, which would use radioisotope thermoelectric generators to provide power in the dark outer solar system. Such a mission could determine the approximate composition of the ocean and reveal the geological engine of this captured world. The study of ocean worlds like Triton, Mimas, and Enceladus forces us to rethink the boundaries of habitability. It suggests that life might not require a warm, sunlit planet, but could thrive in the dark, heated by gravity. Leaving the frozen winds of Neptune, we journey inward, back toward the king of the planets. In the vast expanse of our solar system, among the swirling gas giants and rocky terrestrial worlds, an intriguing world lurks. It is a world larger than the planet Mercury, yet it does not orbit the Sun directly. Instead, it orbits the colossal planet Jupiter. This is Ganymede, the largest satellite in our solar system. Ganymede is a planetary-scale object in its own right. Covered in a thick icy shell, it has attracted scientists for years because it occupies a unique position in planetary science. Its surface is a study in contrasts. Battered, dark regions, scarred by billions of years of impacts, sit alongside lighter, younger terrain filled with grooves and ridges. This tells a story of geological evolution that we are only beginning to unravel. But the most compelling secrets of Ganymede lie hidden from view. Beneath its icy exterior, Ganymede hides a structure that could forever change our view of life in the universe. It is currently the only known moon that possesses its own intrinsic magnetic field, a protective bubble usually reserved for planets like Earth. This suggests a molten, churning iron core deep within. Furthermore, evidence strongly suggests that sandwiched between layers of ice, there is a saltwater ocean containing more water than all of Earth's oceans combined. Today, we take a trip to this distant moon. We will study its recent images and delve into the mysteries these images have begun to reveal. Our narrative of discovery regarding this colossal moon began more than 4 centuries ago, in the year 1610. At that time, an Italian astronomer named Galileo Galilei pointed his primitive, handcrafted telescope at the night sky. He observed 4 distinct points of light aligned with the giant planet Jupiter over several nights. He noticed these points shifted positions, not randomly, but in a clear orbital pattern around the planet. These were the 4 largest moons of Jupiter, now collectively known as the Galilean satellites. Among them, the largest point of light was Ganymede. This observation was revolutionary. It provided the first tangible evidence that celestial bodies could orbit something other than the Earth, effectively shattering the geocentric model that had dominated human thought for millennia. Ganymede is truly the titan among satellites. Its physical dimensions are staggering for a moon, It possesses a diameter of approximately 3,273 miles. To put this into perspective, Ganymede is the largest moon in our entire solar system. It is physically larger than the planet Mercury and the dwarf planet Pluto. If it were orbiting the Sun independently rather than orbiting Jupiter, it would undoubtedly be classified as a planet in its own right. However, size is not the only characteristic that distinguishes Ganymede. Transported to the present day, our ability to study this world has kept pace with exponential technological advances. Modern telescopes, both massive ground-based observatories and space-based instruments like the Hubble Space Telescope, have refined our view, resolving surface features that Galileo could never have imagined. Yet, it was the advent of the robotic space age that truly ushered in a new era of comprehension. Dedicated spacecraft, specifically the Galileo orbiter in the 1990s and the Juno probe currently in operation, have traveled the vast distance to the Jovian system to act as our eyes and ears. They have returned detailed telemetry and high-resolution imagery that allow us to analyze Ganymede as a complex geological world rather than a mere point of light. These missions have revealed a surface defined by contrast. Ganymede is a patchwork of two distinct types of terrain: old, dark regions heavily scarred by craters, and younger, lighter regions marked by grooves and ridges. This duality suggests a turbulent past, where internal forces constantly fought to reshape the exterior crust. An equally tantalizing aspect of Ganymede lies hidden beneath this frozen shell. Based on density measurements and magnetic data, scientists are confident that there is a vast ocean of liquid water trapped between layers of high-pressure ice. Models suggest this subterranean reservoir contains more water than all of Earth's oceans combined. There is a poetic resonance in this discovery. In ancient mythology, Zeus, known as Jupiter to the Romans, abducted a beautiful mortal youth named Ganymede to serve as the cupbearer to the gods. It seems scientifically appropriate that the moon bearing this name carries the largest supply of liquid water in the planetary system orbiting the giant planet. However, the most singular and intriguing feature of Ganymede is something invisible to the naked eye. It is the only moon in our solar system known to generate its own intrinsic magnetic field. This is a trait usually reserved for massive planets like Earth, Mercury, or the gas giants. This magnetic bubble creates a mini magnetosphere inside Jupiter's massive magnetosphere, shielding the equator of the moon from plasma bombardment. Furthermore, this magnetic field interacts with the charged particles of the solar wind and Jupiter's radiation belts to create beautiful, glowing auroras in Ganymede's rarefied atmosphere. These curtains of light, concentrated near the moon's poles, are a sight that would be spectacular to witness from the surface. The question naturally arises, could this distant, icy world harbor the conditions necessary for life? Our understanding of this potential has been greatly enhanced by the daring missions sent to the Jupiter system. One of the most significant of these was the Galileo mission. Named after the discoverer of the moon, launched by NASA in 1989, the Galileo spacecraft arrived at Jupiter in 1995, embarking on a nearly 8-year odyssey to study the gas giant and its diverse retinue of moons. The spacecraft executed several close flybys of Ganymede, taking detailed pictures of its icy surface and, crucially, measuring its magnetic environment with sensitive magnetometers. The data collected by the Galileo probe revolutionized our understanding of planetary physics. It confirmed the existence of the magnetic field, a finding that puzzled researchers. A magnetic field is typically generated by a dynamo, a process involving the movement of conductive, molten fluid such as iron, in the core of a celestial body. This is the same mechanism that generates the Earth's magnetic field. However, judging by the size of the satellite and its age of 4.5 billion years, standard thermal models suggested that the core of Ganymede should have cooled and solidified long ago. A solid core cannot generate a magnetic field. So, how does this small moon sustain a liquid heart? The answer likely lies in a phenomenon known as tidal heating. Ganymede does not orbit Jupiter in isolation. It is locked in a precise orbital resonance with its inner neighbors, Io and Europa. For every one orbit Ganymede completes, Europa completes 2, and Io completes 4. This gravitational rhythm prevents Ganymede's orbit from becoming perfectly circular. As Ganymede follows this slightly elliptical path, Jupiter's immense gravitational pull acts on it with varying intensity. When the moon is closer to the planet, it is stretched. When it is farther away, it relaxes. To understand tidal heating, consider the simple, everyday activity of kneading dough. When you make bread or pizza, you exert force on the dough, pushing, pulling, and compressing it in different directions. As you vigorously work the dough, you are inputting energy into the system. If you were to measure the temperature of the dough, you would notice it begins to heat up slightly. This is because the mechanical force you are applying creates friction between the molecules within the material, and friction generates heat. This is very similar to how tidal heating operates on a planetary scale. In the case of Ganymede, the kneading is performed by Jupiter's gravity. As the moon rotates and orbits, the planet's gravity attracts different parts of the moon with different forces, causing the solid rock and ice to physically bend and stretch. This constant flexing creates tremendous friction deep within Ganymede's mantle and core. Just as with the dough, this internal friction converts mechanical energy into thermal energy. This heat prevents the core from freezing completely, maintaining a layer of molten iron that churns and circulates, thereby generating the moon's unique magnetic field. This magnetic field is distinct because it is embedded within Jupiter's much larger and more powerful magnetosphere. This creates a complex and dynamic electromagnetic environment where the two fields reconnect and interact. For the potential habitability of Ganymede, this is a crucial factor. The magnetic bubble acts as a shield, theoretically protecting parts of the surface and the subsurface ocean from the most harmful high-energy particles trapped in Jupiter's radiation belts. Additionally, the auroras produced by this field provided scientists with a clever way to probe the interior. By observing how the auroras rock back and forth as Jupiter rotates, scientists deduced that something conductive inside the moon was fighting against Jupiter's magnetic influence. The best explanation for this conductive layer is a global ocean of salty water. More recently, the torch of exploration has been passed to the Juno spacecraft. Launched in 2011, Juno's primary mission is to study Jupiter's deep composition, gravitational field, and polar magnetosphere. However, the mission parameters were expanded to include the moons. In June of 2021, NASA's Juno spacecraft executed a high-speed, close flyby of Ganymede, coming within just 645 miles of the moon's surface. This maneuver provided the most detailed images of the moon since the Galileo era. The operational constraints were extreme. The spacecraft's imaging system, known as JunoCam, had a window of only 25 minutes to capture visual data as it screamed past the moon. In that short time, it managed to capture 5 stunning, high-definition exposures. There is an interesting fact regarding this instrument. Initially, during the development phase of the mission, Juno was strictly a physics mission and was not going to be equipped with a visible light camera. It was the project manager, Scott Bolton, who insisted that a camera be included, arguing that we have got to put a camera on this thing to engage the public and provide context. It was indeed a wise decision. JunoCam has not only provided beautiful images, but has yielded serious scientific data. The new images reveal Ganymede's complex and intriguing surface with unprecedented clarity, showing a stark mix of darker regions heavily pitted with craters and lighter regions filled with grooves and tectonic fractures. The Juno science team is currently comparing these images with those taken by Voyager and Galileo decades ago. They are looking for any changes, new craters, shifted tectonics, or changes in albedo that may have occurred over the past 20 years. This comparative planetology allows us to determine if Ganymede is still geologically active today or if its surface is frozen in time. Acquiring these images was a feat of navigation. Juno had to rush past Ganymede at a velocity of roughly 12 miles per second relative to the Moon, and then glide over the tops of Jupiter's clouds at roughly 36 miles per second. Despite these immense speeds and the harsh radiation environment, the spacecraft operated flawlessly. The resulting images give us an unprecedented view of the textures of this fascinating moon. These visuals are key to deciphering the geological history of the satellite. For example, the images clearly show sharp boundaries between the light and dark areas on Ganymede's ice shell, indicating significant differences in the purity and composition of the ice. This helps scientists model how the ice shell formed and how it has been modified by external impacts and internal heat. To better understand what we are seeing, let us take a closer look at the dynamic geologic history of this moon. The surface is divided into two main terrain types. The dark regions are considered the oldest parts of Ganymede's surface. Scientists estimate these areas are approximately 4 billion years old. They are characterized by a high density of impact craters. In planetary geology, the number of craters is a proxy for age. The more craters a surface has, the older it is, as it has been exposed to cosmic bombardment for a longer time without being refreshed by volcanic or tectonic activity. These dark terrains are covered in a layer of dark dust and organic material that has accumulated over eons, absorbing the sunlight and protecting the ancient ice below, bearing the scars of countless impacts. In sharp contrast to these ancient, dark, and cratered terrains, the lighter-colored regions of Ganymede tell a completely different geological story. These bright areas occupy about 60% of the Moon's surface and are significantly younger in geological terms. When planetary scientists examine these regions, they find them modeled with intricate, chaotic patterns of ridges and ditches, known formally as sulci. Some of these ridges rise more than a mile high and extend for hundreds of miles, creating a landscape that looks as though it has been raked by a giant cosmic plow. These furrowed landforms are not the result of impacts. They are thought to have formed as a result of intense tectonic activity. The driving force behind this restructuring is the same tidal heating we discussed earlier. As Ganymede moves through its elliptical orbit, the gravitational pull of Jupiter creates internal friction. This heat causes the icy crust to warm up and become slightly ductile. The crust then cracks, pulls apart, and shears. This process is known as extensional faulting. As the crust stretches, blocks of ice drop down between parallel faults to form valleys, while other sections are pushed up to form ridges. It is a process remarkably similar to plate tectonics on Earth, specifically the formation of rift valleys, but it occurs in a much colder and alien environment, where the rock is water ice and the magma is warm, slushy water. By studying these geologic features, we gain insight not only into Ganymede's past, but also into the universal mechanics that shape icy worlds throughout the cosmos. As we delve deeper into the physical reality of Ganymede, the conversation inevitably turns to biology. Could this icy moon harbor life? While we do not yet have definitive answers, the combination of specific features makes Ganymede a tantalizing candidate for habitability. The primary argument rests on the existence of the subsurface ocean. Models based on the moon's magnetic field and rotational mechanics suggest that there is a layer of liquid water buried roughly 100 miles beneath the crust. This is not a shallow sea. Estimates suggest this ocean could be 60 miles deep, containing more liquid water than all the surface oceans of Earth combined. On Earth, the mantra of astrobiology is simple. Wherever we find water, we find life. Therefore, the presence of such a vast volume of solvent opens up the possibility of biology. The most hopeful scenario involves the ocean floor. If the liquid water is in direct contact with the rocky mantle below, geochemical reactions could occur. We look to Earth's deep-sea hydrothermal vents for a comparison. These chimneys, spewing mineral-rich water heated by the Earth's interior, support thriving ecosystems of tube worms and bacteria that require no sunlight. If tidal heating on Ganymede is sufficient to drive similar volcanic activity at the seafloor, these vents could provide the chemical energy necessary to sustain simple life forms. However, the science is complex. Some models suggest that because Ganymede is so large, the immense pressure at the bottom of its ocean might compress water into exotic, high-density forms of ice, known as Ice 6 or Ice 7. If a layer of hard ice seals off the rocky core from the liquid ocean, it would block the flow of minerals, potentially starving the ocean of the nutrients needed for life. This remains a critical question for future research. Beyond the ocean, there is the atmosphere. Ganymede possesses a very thin atmosphere containing oxygen. It is crucial to clarify that this is not oxygen produced by plants, nor is it breathable air. The density is so low that it is essentially a vacuum. This oxygen is produced by a process called radiolysis, where radiation from Jupiter breaks apart water ice molecules on the surface, releasing oxygen. While not suitable for respiration as we understand it, on Earth, we know of microbes that can survive in extremely rarefied atmospheres, such as those found at the highest altitudes of mountain ranges. Life has proven to be incredibly adaptable. Thus, while the possibility of life on Ganymede remains speculative, the ingredients, water, energy, and chemistry appear to be present. Validating these speculations requires direct contact, yet exploring Ganymede presents engineering challenges that push the limits of our technology. The first hurdle is the sheer distance. Ganymede orbits Jupiter, which sits at an average distance of about 484 million miles from Earth. This vast gap creates a significant communication lag. Even traveling at the speed of light, radio signals take more than 40 minutes to make the round trip between Earth and the satellite. This delay renders real-time control impossible. A human pilot cannot steer a spacecraft or react to hazards joystick style. Therefore, missions to Ganymede must be equipped with sophisticated autonomous software, capable of making split-second decisions without human intervention. Furthermore, the environment is hostile. The surface temperature averages -276 degrees Fahrenheit, a cold so deep it turns materials brittle. More dangerous is the radiation. Jupiter possesses the most powerful radiation belts of any planet. Ganymede orbits within this zone of charged particles. Any spacecraft that visits the Moon is constantly bombarded by high-energy protons and electrons that can fry sensitive electronics and corrupt data. Engineers must encase the spacecraft's computer brains in heavy titanium vaults to shield them, adding weight and complexity to the launch. Finally, there is the challenge of data interpretation. The images and readings we receive are transmitted as binary code across hundreds of millions of miles of empty space. When they arrive, they must be processed and analyzed. There is always a degree of uncertainty. For instance, there is an ongoing scientific debate regarding the existence of water plumes on Ganymede. Hubble Space Telescope data has shown ultraviolet anomalies that could be interpreted as jets of water vapor erupting from the surface, similar to those seen on Saturn's moon Enceladus. Some scientists believe these are genuine cryovolcanic plumes tapping into the ocean below. Others argue they are merely the result of the solar wind sputtering water molecules off the icy surface. Resolving these debates requires better data than we currently possess. Despite these obstacles, the allure of discovery drives us forward. Our exploration of this fascinating satellite is far from over. In fact, a new chapter has just begun. The major space agencies of the world have aligned their sights on the Jovian system. Leading the charge is the European Space Agency's mission, known as JUICE, the Jupiter Icy Moons Explorer. Launched on April 14th, 2023, from the Guiana Space Center aboard an Ariane 5 rocket. This massive spacecraft is currently on a long, looping trajectory through the inner solar system to build up speed. When it arrives at Jupiter, JUICE will perform detailed observations of Callisto and Europa before entering orbit around Ganymede itself. This will mark a historic milestone, the first time a spacecraft has ever orbited a moon other than our own. JUICE carries a suite of 10 advanced instruments designed to peel back the layers of the moon. Key among them is a radar sounder capable of penetrating the icy crust to a depth of several miles, potentially allowing us to see the structure of the subsurface ocean directly. Magnetometers will measure the induction of the moon's magnetic field to confirm the salinity and depth of the water. Beyond JUICE, the scientific community is already proposing even more ambitious concepts. Engineers are drafting designs for landers that could touch down on the fractured ice to sample the surface chemistry directly. There are even long-term concepts for cryobots probes designed to melt their way through the thick ice shell, carrying autonomous submarines that could eventually swim in the alien dark of Ganymede's ocean. While these missions are still in the conceptual stage, they represent the bold, innovative thinking required to unlock the final secrets of this world. As we look to the future, the significance of Ganymede becomes clear. It is more than just a moon. It is a premier laboratory for planetary science. Its unique geology, its intrinsic magnetic field, and its potential for a hidden, habitable ocean make it a cornerstone in our ongoing quest to understand the solar system. By studying Ganymede, we are not just cataloging a distant rock. We are learning the fundamental rules of how worlds evolve, how oceans survive in the cold, dark, and ultimately defining the parameters of where we might find company in the universe.